But yeah, at least in terms of the format of the exam, we try to make it pretty standard so that you know what to expect. Like, did people generally feel like they were not blindsided by the exam format or kind of what they were expected to know?
Definitely.
Okay. What other thoughts do people have about the exam? Because I know everyone has thoughts. It's just, are you willing to share them? Wes? And everyone said, no, I am not willing to share.
I don't know. Personally, I felt the academic questions were
Yeah, was.
my main result.
Well, I think that the main questions that we are thinking about when we're making it is, do they know what to expect? Are the kind of expectations clear? And then overall, did the exam seem fair? Like, did it seem like a difficulty level that was fair, or do you think it was too hard? I don't think anyone thought it was too easy.
I think if we were actually taught the subjects, like lecture would be helpful.
I don't think we were well prepared with these things we were given to learn.
For what types of questions?
Every single question.
If we had to like
Like
I
some
had
of
to
them.
learn all the one.
I think like mechanisms could have been like gone. I think we could have learned about that a little more in depth. I don't feel like we were really taught mechanisms. I think I had to do most of the work on my own, which I can do, but it's like ended up with most of the subjects.
Hmm.
Personally,
No,
maybe
I-
other people had different experiences.
I agree with you with the mechanisms. I think they're very. You do have to like get the hang of like what comes first, and then this goes there. And just personally, also when I was in practice exams and this and that, I felt kind of lost in terms of like, okay, where do I start now? Where do I go? It's just, and I
Yeah.
don't think that was we ever did mechanisms like in lecture, or like if we did them, we weren't like, or at least maybe not in lecture 3, maybe
Yeah.
a little bit more in lecture 5. Just said, okay, like this is like a lone pair push, and then like for example, I didn't know that like when you have an acid first string, you have to have the acid attack. Just these small
Yeah.
subtleties, maybe the sort of skill
Well,
have to build up.
And one thing to kind of comment on that, it's tricky because in lecture we do the mechanisms. Like, we do them with you, and you see the mechanisms and have a chance to kind of ask questions. But it's like we're teaching you how each piece on the board of chess moves. And then on the problem set where you don't have like the answers being given to you by us, you are having to play chess. And like that is a big gap that requires a lot of legwork on your own. And that is true of every like organic chemistry class. Like, the legwork of getting to where you have a reaction and then being able to use the reaction, that is the hard part about organic chemistry that has historically been hard and is like everything. And so it's kind of like, how can we prepare you to do that? Because that process is going to be different for everyone else. So if you have like suggestions for like how we should approach the reactions with you, like what would you change to make it better to learn it?
Like we need to do a lot of teaching to us since outside the class would be good to have like, which it's like I think it would be good to have like a set of resources that might be helpful, or like it's like I was kind of just like Google. Like it's like I don't, and it's like different resources will give you different answers.
Mhm.
So there's not a lot of consistency. And then
So were like lecture and section notes not your kind of first reference for trying to work through and learn things?
the lecture notes I don't think covered all the types of questions that I saw when I was doing practices. And it's like that, I think that's just the nature of it, where it's like it can
Yeah.
be so different. But I don't think it's being good because I don't know, I need to have a lot of multiple
Hmm. Heard. Yeah.
I think the problem is now that like not all the if you go into lectures in different topics, all the lectures are there, but they're not told to you that they're there. And they make it clear that this is like the lecture notes are everything you need to know and they're there. I like not to like hate on Tim or like anything. I just think the principal when explains it, like in lecture 5, she was like, this activates this, and like why the reason why behind everything, and that really helped me like conceptually, because I was talking to a T a lot yesterday about like all this stuff, and she was like, you should never have to memorize ortho, you should already like be able to understand the why behind it. And I personally, when Tim was going through it, I don't know if it's the first time we saw mechanisms that he was struggling, maybe once you're in it, I have another background understanding from like her explaining like this is the most negative, this is the most positive thing, so they interact with each other and then like they apply it to every question. Versus like I feel like Tim was like, we're gonna learn how to listen now. And because he's so like knowledgeable about the topic, he just becomes instinctive in him, but not to us yet.
Like I think he helps, she helps conceptualize the
Yeah.
questions in a better way that we can like apply to other.
I
agree.
applied it to study for the
I
exam where
agree.
she said,
And it's
I
like,
was
wow,
like,
like I wish we had this
But, like,
lecture
it was
like
on
way
Tuesday, and,
before.
like, 48 hours before the exam.
Well, and I think also, again, I would give some credence to the fact that it's your first reaction learning, or lecture learning reactions in lecture 3. And so you didn't know what was important or to pay attention to as much. Whereas when you saw Serenia's lecture 5, you had already seen, worked with, and studied reactions, and you knew things to look out for. Like Tim, when he was doing things, was explaining them, but he didn't, like different teachers explaining them different ways, they don't always kind of pop out the same kind of importances. Like different people highlight different things.
I have to respectfully disagree, like, I mean, he's a work teacher and everything.
I
I'm just saying, like, I'm just being honest with that, but if he actually explains it, there's like an easy go over, like, if he just speaks through it and doesn't, I mean, in my opinion, he doesn't really take the time that the person who does to explain why they're doing it. And I think that's a huge part of learning, which is why I had such trouble with I would explain to myself why I'm doing this and that.
Well, yeah, and maybe I'll share, like, I have also been a disgruntled organic chemistry student. My, like, OChem classes that I first took, my first OChem 1 and OChem 2, I thought the professor was horrible. I hated I stopped attending lectures. Like, I fully, for OChem 2, like, after the first unit, I just did not attend any of the lectures. And I found the OChem as a second language book, and I taught myself organic chemistry. And, like, I think that there are a lot of differences in the way different people present it, and also in the ways that people take in the information. But I do think, at least I will say about all the course staff, I think that they care, and I think that they want to help, and I think that they are trying actively to improve things and make it more engaging. And so I do appreciate the feedback, and I definitely understand the frustration with it. I think the big thing to think about now, and the big thing for exam 1 that I will encourage you to take the score as, is it's a diagnostic of kind of not really your mastery of the material, but of your study methods, and kind of like what is going on in the class in terms of getting the material under your belt to where you can answer these questions. And so I think it should be a pretty kind of clear assessment of like what study strategies are working well for this class, for this context, and which are going to need to change a little bit based on the types of questions that we are asking and kind of the demands of the class. And so between exam 1 and exam 2, you have time to try out new study methods and like take a risk and see if something will be more helpful. Between exam 2 and the final, you will not really have enough time to adjust. Like it will be 1 week between exam 2 and the final, and then you're kind of locked into whatever study strategy you're using. There's only one like lecture difference between exam 2 and the final. But I did just want to kind of say that like the first exam is 15% of your grade. It's not a huge bit. 15, yes. Oh, no, yeah, it's not a huge like portion of your grade. And I've seen many students have a rough exam 1 score, come back and do a really strong performance to finish out the course. So again, I would encourage you to take it as helpful information and feedback for how to kind of proceed. In terms of timeline of the exam, we are going to finish our grading on Sunday. So we will have all the grading done. Monday, the staff will get together and we will discuss kind of the data and the grades and see if there's anything that we want to change in terms of like point values. And then we will release scores on Monday night. On Monday night when we release scores, I don't know the exact time, we will also release the answer key. The blank version is already on Canvas. And then regrade requests will open then, and they will close next Friday. Regrade requests have to be for a valid reason, and valid reasons include 1, the answer key says what I put, and you've graded this incorrectly, or 2, based on this material that I have been taught, this should be a valid answer. They should not be. I think I deserve more partial credit for this. Like we just can't kind of order those requests in a way, and like we have to kind of grade fairly for everyone for the question. Yes, are there any other kind of exam questions before we move into a real section? They used to be 2-hour exams, but they used to be 12 questions.
I didn't like go with the timing, like I did get to like I had like 10 minutes left to go over some things, but like I just couldn't go over as much as like I wanted to go over, and like I think I think this test was very different in the sense that we had like the first like half of the exam was not really like OChem, and it was OChem, but it was more like gen chem.
Lots of the skills, yeah,
So
that
like, I
concept.
think that part I would really like to like, go over again because those were more like conceptual questions than like once you get the answer for a question in the formulas, you can like proceed with it and like you can
Yeah.
finish. So that's why like, I think 10 minutes like would be the world of difference for the first part of the exam.
Yeah, it's something where I can see it, and I think that that's unlikely to change because part of the skill is being able to do it quickly, and that's why the practice exams, taking them under time conditions, is so important to build up that speed and see kind of the level it needs to be at. But like, you're right. I think everyone's scores would be higher if we gave you 20 minutes more. Like, yeah.
You mentioned that you're gonna go over them like together with staff, and that if certain like if a big chunk of the class did very poorly on a question, you might reduce like the number of points it's on.
It's a thing of like, let's say there's a question and there's a mistake that we've graded as a 3-point deduction, but then 40 people in the class made that mistake.
Okay.
Then we might be like, actually, there's got to be a conceptual reason for why so many people have done it this way. Maybe let's kind of reevaluate the logic in it and actually only take off 1.5 points or something. And that can happen sometimes. It's also like each of the TFs and staff are going to grade different questions, so we're going to look at what each other graded and how they kind of counted off points to see if we agree with that assessment or if we should have taken off more or less.
Okay. But you wouldn't like change the overall number of points that like one of the questions you got.
Correct. Yeah. Cool. Are you ready to jump into lecture 5 stuff? Well, we have kind of 4 big things that we are going to hit on. First up is amines and enamine reactions. Second is redox line reactions. Then we have the carboxylic acid derivative questions and amino acid chemistry to round it off. So let's jump into it with amines and enamines. So first off, we have some new functional groups. These are functional groups that were not on exam 1, and you are not going to have an explicit exam question where you're going to have to circle these functional groups or anything, but these are going to be helpful to know and identify for working the questions that are related to these like mechanisms. Like if you are not able to name the compound or name the functional group, it's going to be a lot harder to kind of work with them and summarize the logic when you're studying. So we had a carbonyl for carbon-oxygen double bond, and now we're just going over and doing the nitrogen version. So the nitrogen version of a carbonyl is an imine here, a C-N double bond. And then typically it's going to have some kind of alkyl group off the side because nitrogen likes to have 3 bonds. Then one that we saw less often was an enol, which is an alkene and an alcohol together, enol. And it's one functional group because there's some resonance between it. The nitrogen version of that is called an enamine. So enamine. Like, be nice, don't be mean, enamine. These names all sound super similar. Amine, enamine, amine. So it's really easy to get like tripped up words-wise. Then if you think back to section 2, we introduced this nomenclature for amines of like how we label an amine as primary, secondary, or tertiary. And it's based on how many carbon things it's attached to. So like this would be a primary amine, and then this one would be a secondary amine. So these are the other kind of big players. And then if we take an amine and we protonate it, or we have kind of 4 bonds to the nitrogen, we call it an aminium. An aminium. And it's kind of like ammonia to ammonium. The IUM ending means positively charged. This is going to be like a key intermediate that we see. And then the other one here is called a hemiaminal. So a hemiaminal is partially amine. That's where we get the Mn from. And then OH here is the hemi, just like a hemiacetal. But I remember where I was the first time I heard hemiaminal. I was in Science Center, 3rd floor, a classroom in an exam review for Chem 30. And I heard the TF say hemiaminal, and without a beat, in my head, I just went Gesundheit, because I was like, that's an involuntary utterance. That just like spilled out of you, hemiaminal. That's nonsense. This is crazy. We're just making things up. It really like broke my brain, and at that point in the review, I put my pencil down and I just said, okay, okay. And so, yes, every time you see it, feel a little bit crazy and like, what are we doing? But also, this is an intermediate that's going to be formed in all of these reactions, so it is good to know her. The last like little piece of nomenclature and like relative kind of position naming has to do with the position away from the imine. So let's say we had an imine here, or we had like a carbonyl. Either one works. We call the carbon that's right next to the carbon of the imine bond an alpha carbon, the one that's right next to it. And hydrogens that are on an alpha carbon, we would call alpha hydrogens. Then if we go one more away, that carbon is called a beta carbon, and you have beta hydrogens on it. This is something that's going to come back in like lecture 10, so it will be back later, and actually I think it will come back in lecture 6 as well. So I want you to kind of have seen it, but it's also going to help us with labeling some things here. So again, I know I'm just kind of dumping information of new functional groups, but this is going to be a resource to look back to. Yeah?
It can be any amine, right? So
Yep.
first, second, or third.
Yes.
And is there a hydrogen as well, or is there no hydrogen?
It depends. This R could be hydrogens or carbons.
Okay.
Yep. Cool. So it's amine and alcohol. So the big key idea for these kind of reactions here, there are only a few reactions in this little family, are the type of amine that you use determines whether you get an amine or an enamine. So if you use a primary amine is going to go over here and form an imine. Whereas if you use a secondary amine, that is going to form an enamine. And it seems like a small difference, like they're both amines, right? And so the only way you're going to be able to predict the right one that forms is if you kind of associate secondary with enamine, primary with imine. And we'll talk about why secondary goes on to form an enamine in a minute. I know, it's a lot. This is the one where I like most often misspeak too, just because they all like blend together. I know. There's one typo in it, and it's because like the chemistry notation software doesn't like when I put R's. There's an extra hydrogen there that should not be there. So just mark out that hydrogen. Apologies, I did not catch it. So I'm going to talk through the mechanism briefly, but this mechanism is mostly made up of steps you've already seen before. And so especially after the first exam, you should be more comfortable with a lot of these steps of like acid-base or proton transfer and a nucleophile attacking carbonyl and a lone pair push. This whole lecture is basically combinations of those steps. And so it's just putting them into the right order and context. So you start off with the amine attacking the ketone or aldehyde. You make a little tetrahedral intermediate. We do a proton transfer where we put a hydrogen on the O over here and we remove one from the nitrogen. And we make our neutral hemiaminal, gesundheit. Then what we're trying to do at this point is we are trying to kick off an oxygen because we have no oxygen in either one of our products, right? So we need to make her leave. The only way we know to make her leave is to do a lone pair push. And to help us do this lone pair push, we are going to protonate it to make it a better leaving group. So from our hemiaminal, we protonate the OH, make it OH2+. Now it's a good leaving group. It's easy to kick off. We can push down and kick it off. And now we're at an iminium ion. So carbon-nitrogen double bond with a positive charge. And this is the same exact mechanism for both the enamine formation and imine. They do all the same steps up until this point, and then they only differ in the last step. So let's see how that structure of the amine affects what it forms as the final product. So if you start out with a primary amine, then you are going to have a hydrogen on this nitrogen that is positively charged. And so to get your final product, you can just deprotonate that hydrogen and wind up with a neutral amine. So primary amine, we just stop at the imine here. When we have a secondary amine, though, we're going to have two carbon groups. Like these could be like two methyls or one methyl, one ethyl or something. And we don't have something that we can easily deprotonate on the nitrogen, right? But it still has this positive charge. And we typically like to have a final molecule that's going to be neutral. So what we're going to do is we're going to go down and go to our neighbor, the alpha carbon, and we are going to deprotonate an alpha hydrogen. When we do that, it's going to push electrons in to make a carbon-carbon double bond and free these electrons to go up to the nitrogen. And with that, we make an enamine. So, yeah.
So even though that nitrogen is double bonded with carbons, it's not included, it's an amine because it's attached to an aldehyde.
Are you talking about the difference between an imine and an amide?
Yeah, I thought amides were double bonded with carbon, but then it's just not connected to the rest of the.
So, amides, A-M-I-D-E, are when you have an amine next to a carbonyl. Yeah, so you still need like carbon-oxygen double bond, whereas an imine is a carbon-nitrogen double bond. Yeah. So this kind of alpha deprotonation, it's kind of weird, it looks a little bit new, but it really is acid-base, just kind of with some resonance things going on here. You saw some arrows kind of similar to this in a conjugate addition, where you had to do at one point a alpha protonation, where I think it was like O-, you would push down, and then this would go and grab a hydrogen, and it would add it at that alpha position. So that was an alpha protonation. This is an alpha deprotonation. So the mechanisms here, again, a lot of the learning of mechanisms and making sure it kind of makes sense internally is the studying that you have to do on your own, and so I'm not going to kind of belabor it. I do want to talk a little bit about the hydrolysis. So to go backwards, you use H3O+. So to go from an amine or an enamine back to the ketone or aldehyde, H3O+. And why do we need to use specifically H3O+ and not just any old acid? Yeah, I tried to kind of like highlight it here. You need something to supply this oxygen. And so H3O+, we're going to have an H2O molecule, and that's going to be what adds the oxygen that becomes part of this ketone or aldehyde. Yes, the other thing to think about with the line reactions is start making and thinking about your fake mechanisms. Like if I were to go from an enamine to a ketone aldehyde, this direction, what kind of fake mechanism would you come up with so that you could write the product? Well, so when I think about break, I think about like fully disconnecting. I kind of just want to pave over the double bond, make it single, right? And then what do I fully want to cut off? The nitrogen. So we cut off the nitrogen, add a H here, and then pop a carbonyl on the other side. And that would get us our ketone aldehyde and our amine. So again, be thinking about these as you learn each new reaction, and it's a tool for you to write the product. I'm not going to go through the reverse mechanism because it's truly the reverse steps, but in the same way that the Ford one, it was all the same and then it had one different step at the end, the reverse reaction has one different step at the beginning that just undoes the last thing. We either protonate at the nitrogen or we protonate at the alpha position. And then all the steps are the same from there. And notably, you do form the hemiaminal going backwards as well. So what I'd like to do is look at one of the questions on the problem set, and I'm also going to try to get through some challenge problem questions with y'all just to like help knock out some of the P-set. But I have chosen a hard one to do with you. So we have ketone aldehydes. This is page 8 in the problem set. And then what type of amine do we have, primary or secondary? What determines whether a amine's primary or secondary? How many carbons it's attached to. So if it's attached to here, this is attached to one carbon, this methyl group, then what is it? Primary. So a primary amine and an aldehyde over here, what would we expect the product to be? An imine or an enamine? Imine, because we know primary is going to form an imine, whereas secondary is going to do that last step and go all the way to enamine. So let's draw real quick, or I'm going to draw. You don't draw this yet. what the product of the amine formation should be. So I'm just going to pick one side of them because this is a symmetric molecule. And this one on the left, I'm going to make into this amine. Where I just, again, my fake mechanism is I erase the O, put a nitrogen, and then whatever's on the nitrogen, so the methyl. So going from this starting material to this is straight up regurgitating the arrows of like the amine formation mechanism. So the one that I have kind of printed on the other slide. And so what I want you to take like 2 minutes to do is to try to draw the arrows to form this intermediate. And then afterwards, we will do from here to here to the end altogether because that's a little bit weird.
But does it react with both?
So not at the same time. It could react with this one, and then once it's done that reaction, react with this one, but it's not going to react with them at the same time.
So why are you assuming there's only one? Like what if there was more than one?
If there was more than one, we would first form this and then do the other one. So no matter what, we know this is formed.
Yeah.
Yes.
So is there like a mechanism?
Yes,
Okay.
mechanism fully. So again, I want you to draw out the steps, and it's just a basic amine formation reaction to get to this structure, and then we will do the rest together.
So now what about proton transfer? Can you see one, see one?
One thing to be careful of is a proton transfer can only transfer like one proton off, one proton on. So if you tried to go from here all the way to here, this is a change of like you're adding 2 hydrogens there and you're removing 1 here. You couldn't go directly here. So, yeah.
So first it's a proton.
Sorry?
So first you put in the all
I would do the proton transfer first because then you get to form the neutral hemiaminal. And that's like a stable neutral intermediate because it's no charges. And then from there I would protonate the OH. Different classes and different like people have different preferences for those protonation steps, and it's not super important. But my kind of guiding light is the hemiaminal and all of its silliness.
But the oxygen gets proton from what the solvent, which would be like what would be
Just water here.
oh, just from the water. Because this is basic emissions, right?
We're pH around 5-ish, so slightly acidic, slightly basic.
So benzophenate hydroxide.
Yes, and again, the identity of that molecule doesn't really matter, which is why in mine I just put H-sol.
Okay.
Yeah. The other way to think about it, Angelica, is in the first step, you form something that has an O minus, right?
Mm-hmm.
So if that O minus can form, an O minus on an OH could form. Yeah.
And just like the furthest, like, since we have primary, we would just have the N connected to two H's and one R instead of one H and two R's.
Yeah. So just like 30 more seconds to get through those arrows. Again, the arrows should be almost verbatim what was presented in the lecture and here in the section notes. Okay. So let's start from here now and try to get to the product, which is going to be the weird stuff. So what functional groups do we have in the product? Sorry, in this product. Amine, or the pronunciation. So if it's alkene, enamine. Enamine. So yeah, we have an enamine, and it's kind of like we have two enamines here, one on either side. And enamines normally happen with what type of amine? It's normally a secondary amine and a ketone or aldehyde. Well, we have an aldehyde here, but we don't have a secondary amine, right? One thing that this is the weird step, this is the thing that like you only can figure it out by knowing that you have to form a ring. And if you form a ring, that typically is a tip-off that you've done an intramolecular reaction. So the molecule has reacted with itself. That's the only way to really figure this out. But do you see how this structure right here, this imine, could kind of look like a secondary amine with bonds to two things and like a lone pair that could go and attack? So, like, there are some people who would call that a secondary amine because it's attached to two carbon things. But here, because it's a carbon double bond, the better label is amine. But it does have a lot of structural features similar to a secondary amine. And so, why don't we treat it like a secondary amine doing an attack and see what happens? Especially since we know that it has to do something intramolecular. So let's have that lone pair go and attack our carbonyl and push up. Now, this is the type of step that it's hard for y'all to draw what the next product is, right? Because you're forming a ring and like you have to kind of move it around. So I want to show you a strategy that I like to use to break this down into like concrete steps and make it easier. So what I'm going to do is I'm going to number all of the atoms that should be in this ring I just formed. So I know it starts with the carbonyl, 2, 3, 4, and then the fifth atom in the ring is going to be the nitrogen. So I've numbered those. And then all I'm going to do is I'm going to draw a little pentagon with a nitrogen because I know it's a 5-membered ring and one of the members is a nitrogen. And it doesn't matter the mapping it on yet. I'm just drawing the pentagon, putting a nitrogen, and then we're going to make it reflect what it should be. So if I go on here, I can then just assign, because I'm building this molecule, 1, 2, 3, 4, 5 to these positions in the ring. And now I just need to make sure that everything that was there before, it has the remaining things it needs on it. So like, for example, carbon 1, we attacked carbonyl and we pushed up here. So what should we have on carbon 1? An O minus. Yeah, and we should also have a hydrogen, right? And that hydrogen, I can just imply here. So I'm just going to imply it because we're not going to do much with it. Okay, so we have an O minus. Is there anything special on 2 and 3 that we need to make sure to add? No. 4, what do we need to have? Arbitrary. You could have done it counterclockwise. What? You need a positive charge on the nitrogen, but right now we only have 2 bonds to nitrogen, so we're missing some. So what do we have between 4 and 5? A double bond, and we didn't do any arrows that broke that double bond, so we still need to have it. And then we need to have that methyl on the nitrogen. Yeah.
How do you attack the nitrogen attack the carbon right versus the oxygen attack?
What oxygen?
Like the aldehydes oxygen. Because I would have done
Like this
ox-
attacking this?
No, attacking the nitrogen.
Oh. It's because amines or nitrogens are better nucleophiles. Like when you go back to your MO theory, you have like a lone pair on nitrogen and a lone pair on oxygen. And if you were to rank these, which of these is higher in energy? The nitrogen. And it's because the oxygen's more electronegative. So the lone pair on the nitrogen is going to be the better homo donor than the lone pair on the oxygen. Yeah. Cool. Okay, so we made our right structure here, and then we need the positive charge on the nitrogen. And then we have some charges here, so let's maybe neutralize it as our next step. So why don't we go and grab a proton and neutralize our O minus. Okay. And now we're stuck with this kind of iminium here, carbon nitrogen double bond, and we have a positive charge. And we have no easy way to just deprotonate the nitrogen and make it neutral, right? Because it's attached to carbons everywhere. So what was our strategy that we did to deal with this situation in our kind of amine and enamine mechanisms? If we had a nitrogen with a positive charge that we couldn't deprotonate the nitrogen, where did we deprotonate? We protonated, let's see, it's this scenario, right? We have a carbon nitrogen double bond, we don't have any hydrogens on it, and so we went to the alpha position and we deprotonated there and made an enamine. And hey, this reaction, we're trying to make an enamine, right? So let's find our alpha position and deprotonate. So I'm gonna number these real quick. 1, 2, 3, 4, and 5, I guess. Which of these is our alpha position? 3. And it's because we need to be one next to the carbon and the carbon nitrogen double bond, and that's our alpha position. It's not having to do with the one next to the nitrogen. So this is our alpha position. We're going to draw in one of our alpha hydrogens that's already there. We're just explicitly drawing it. And then our solvent, you can write H2O if you want, is going to come and deprotonate at the alpha position.
How can you get a positive charge there then if you deprotonate it?
What?
If you take away the hydrogen, right?
Yeah,
How come that carbon doesn't have a positive charge?
because we're making a double bond.
Yeah, but still it has.
It has 4 bonds before, it has 4 bonds after.
Oh.
Yeah, no, you're good. Okay, so we've made one of our enamines. That's good. And then, what functional group is this that we have? We have the enamine, but what else do we have? The hemiaminal. She just keeps popping up in these reactions. And again, when you're able to kind of like spot her as like, oh, she's a player, I know what to do in this situation, let's look at what we did with the hemiaminal before. So hemiaminal, we protonated the oxygen, and then lone pair push kicked off water. Let's see, in the context of this problem, do we need to kick off an oxygen? Like, is this oxygen in the final product? It's not there, so we do need to kick it off. So let's try that. Let's try protonating the OH and then kicking off water. It depends on which direction you're going in the hemiaminal. So if you were doing hydrolysis, you wouldn't lone pair push off water. You would do yeah, you would,
Add water and then,
yeah.
but like it's always gonna be like one or the other, typically.
Typically, yeah. Yeah. We have OH2 plus now. And then we can lone pair push, kick off water. So we are rather close now. We have all the double bonds we need, or we have 2 double bonds at least. And yet again, we are at the situation where we have an iminium. And can we do anything to deprotonate this and make it neutral?
Same as we did before,
Yeah, we can deprotonate at the alpha position. And if we look at it, the thing that we need to form is like this double bond, right? So it would be a double bond that was kind of in this position or this position. Right now that position has 2 hydrogens on it, but then on the actual molecule only has 1. So that's another clue that tells us that we have to deprotonate there. So I'm going to draw out another hydrogen there, and then we just deprotonate it. And that takes us to our final product. So I definitely chose to do a hard one with you that like does some weird things. But truly, the first whole part of this was straight up just the lecture notes version, the kind of plain Jane. And this was the only step that wasn't a step you've seen before of an imine doing a nucleophile attack. All the other steps are protonations, alpha deprotonations, and then lone pair push off water, which you saw in the base mechanisms and you've seen in like acetal mechanisms. So these types of steps should start to feel useful to you as the tools that you should have going into a problem like this. And then the tricky part is figuring out how to use those tools. And a lot of what we did is we kept looking at the product and seeing what bonds we need to make and break. And that's going to kind of guide us. Okay. Cool. So that's all I have for you on amines, enamines, and then the rest I think that you'll be set up to kind of study and learn on your own. Let's jump, yeah, Danny?
When it says solution, is it always going to be clear as to what the solution actually is, or is there something just solution?
So this is the thing that I need to double check with on Tim, because normally, like in lecture 3, he introduces the notation of Sol for something in the solution. And he just didn't this lecture 3. I don't know why. And I'm pretty sure that y'all will be able to use the Sol abbreviation, because truly, this is not something we care about. Like, she is a side character. The main character is the intermediates that we are drawing to try to figure out the transformation. And so in the past, students have always been able to use the Sol kind of abbreviation as something grabs it. But Serinya comes from a background that has a little bit more specific notation. Like specifically with like the Sol and the source of protons, she doesn't often write just like H+. She will write a protonated like alcohol or H3O+. And like that is like a more structured system. That's the way I learned it originally. But again, it places a lot of emphasis on knowing just what else is in the reaction and these kind of side products and side characters that we don't care about as much. And so I'll check with Tim to see and double check, but I'm pretty sure that you'll be able to use Sol.
Or is it usually water in these cases? Or
Well, in this case, you can kind of like look at the reaction, and yeah, our solvent is water.
okay.
Yeah.
So with context, it would be just
Yes. Or you should be able to figure it out with context, even if it's not clear.
okay.
Cool. So our next big kind of topic are the redox line reactions. So do you remember from Gen Chem doing the thing of like oxidation numbers, and like there were all these rules you had to remember of like a hydrogen has an oxidation number of +1 and oxygen is -2, and like there were like calculations and things that you had to do. Do you vaguely remember? So we don't care about that. Organic chemists are lazy. We need like a simple system, and we really only care about the oxidation level of carbon, or oxidation number of carbon. So we've made this kind of different system called the oxidation level system. And the oxidation level of a carbon is the number of bonds it has to something electronegative. So oxidation level 1 includes things like alcohols, amines, and alkyl halides. These have one bond to an electronegative thing, so all these carbons are oxidation level 1. Oxidation level 2, you have double bonds, so 2 bonds, 2 electronegative oxygen, so ketones and aldehydes are here. Oxidation level 3 are the carboxylic acid derivatives, or CADs, that are the subject of this lecture. And then oxidation level 4, there really only are 2 that you'll see, and that's CO2 and carbonic acid. And we don't really work at this oxidation level. Nature does, and so when you get to Chem 27, you'll kind of see these a little bit more. But these are kind of our oxidation levels. So why does this matter? Why are we talking about it? It's kind of because carbons at the same oxidation level react similarly. So you know how in lecture 3, every reaction that we taught you pretty much, you could do either ketone or an aldehyde as the starting material? It's because they're the same oxidation level, so they react very similarly. And just like that, the reason that we teach the CAD reactions as a group to you is because they're all at the same oxidation level, so they do similar types of reactions. So it's a really helpful tool for us to know how a thing is going to react to kind of clock its oxidation level. The other thing is we need to be able to move between the oxidation levels here. So these reactions that change oxidation level are called redox reactions. And if we go up in oxidation level, it's called an oxidation. And if we go down in oxidation level, it's a reduction. So if I went from level 1 to level 3, is that oxidation or reduction? Oxidation, we go up. If I went from 4 to 2, oxidation or reduction? Reduction. Pretty easy, but it's helpful to have, put a name on it and to kind of have that down pretty cold. So let's meet the players here for our oxidation and reduction reactions that are going to help move between levels. So first up, we have chromium trioxide. She's looking very symmetric today. She's very trendy. You might find her at New York Fashion Week, sporting the latest trends. She has sidekicks that she uses. So she has pyridine, which is the solvent here that acts as like a general base, and you can abbreviate it PYR, or water. And then, you know him, you love him, lithium aluminum hydride, also known as toxic masculinity here. He's going to be our main reducing agent, whereas chromium is our main oxidizing reagent. So these reactions we are going to use a lot. These are probably the most common reactions that you are going to use for the rest of the course because they're so useful in changing between these functional groups and moving oxidation level. And so this is going to feel a bit weird, but can we give them a round of applause for the heavy lifting that they are doing? Thank you. Chromium trioxide, lithium aluminum hydride, thank you for your service. Wow. So let's see what they actually are doing. Here, for oxidation and reduction reactions, let's start off with oxidation. What are the oxidation levels of everything here on the left side? 1. Why? Exactly. We only have 1 bond from our carbon to an electronegative thing. Okay. And then, what oxidation level are these two? Can I see on fingers? 1, 2, 3. Oxidation level 2. Good, because we have 2 bonds.
The double bond, right? Or the oxygen is that twice too?
Yeah, 2 bonds. And then here, what oxidation level is the carboxylic acid that we go to? Fingers? Nice, 3. So, we use chromium for all of them, but when we are going from oxidation level 1 to oxidation level 2, we use pyridine. So pyridine goes from 1 to 2. And then if we go from oxidation level 1 to 3, we have to use H2O. Does anyone want to venture a guess of why we need H2O? Yeah, like here, it starts off with 1 oxygen that becomes this carbonyl oxygen. But then this other oxygen has to be introduced from the water. So the water introduces it. Now, all of these are reactions that you don't need to know the mechanism for. There is a mechanism, it's just a little bit complicated, and working with metals, metal mechanisms are a bit much to keep track of and is not really what you're gonna need going forward. And so I really think of it as chromium gobbles up hydrogens and makes double bonds. Truly, you just need to know a fake mechanism of how to write the product. And again, this is where, like, when we just say learn line reactions, this is where there's something that is a little bit more memorization-y. Like, you're not understanding the why of each arrow of this. But, like, to use this in synthesis and to use this as a tool, that's what we care about you knowing, rather than knowing every step of every reaction. So, let's say you want to go from here to here.
Yeah.
You would use chromium trioxide with water.
Oh, so 2 to 3 is also.
Yes, and it's because an aldehyde's an intermediate in this reaction. And so if you want to just go from an aldehyde to a carboxylic acid, you would use chromium with water. Cool. Then our reduction line reactions. Again, these, you've done some reactions with lithium aluminum hydride before, but you've done the easy ones with lithium aluminum hydride. And with these, she does some complicated things that we're not going to get into, where like the aluminum associates and like is coordinated. So we're not going to get into the mechanisms for this, just line reactions. What are the oxidation levels of all of these? 3. And then what are the oxidation levels of all of the products of lithium hydride over here? 1. That's the whole thing with like lithium hydride being a really strong reducing agent. It's going to take things typically all the way to 1. And you have to use this stronger one if you want to react with something at oxidation level 3. You already saw that with like, you couldn't use sodium borohydride to react with esters, but you can use lithium hydride. The other thing I want to flag with this is these bottom 2 reactions right here are the only 2 reactions in this entire course that make amines. So if you are seeing a box problem or a synthesis and there is an amine there that you have to make, these are the only 2 reactions that you will ever know to make an amine, which is kind of nice. Like, I love, I was going to phrase it in a way that sounds mean. I love, like, using your ignorance to your advantage. Of, like, oh, I'm not responsible for anything more than this, so I know it has to be one of these 2. Like, that is very valid, and it's really helpful.
So you always need a nitrile or an additive.
Exactly. Good. So let's see these in some line reactions and kind of put these to use. So I've gathered some line reactions. These are from challenge problem 3 and from Skill Builder on page 6. And they're not in order, so just pay attention to the ones that are up here. And I want you to try working through some of these. And each one of these is going to use a redox reaction at some point, either an oxidation or reduction. And they also will combine some other reactions that you've seen. So what functional group is this? An enamine, yes. So that's going to use the amine-enamine reactions that you saw just before this. And then what functional group is this? I know you all know this. Acetal. So this is combining redox with the lecture 1 stuff that we've done. I would say skip this top one, start with these, and then come back to the top one. The top one's a little bit trickier. But I will kind of circulate and get some questions. Yeah. I haven't plugged either one in a while, I think. Abby, it just takes me a minute. Alyssa, Lauren, the E's, yes, the E family. You got it the best. Nelson? No, I'm working. I'm making a spreadsheet of like, these are the names that I don't have a face. I need to figure out who they are.
We'll have to change seats one day.
Truly. There are 8 students, I still have no idea who they are. So I'm gonna find out. What?
No idea who they are. I think it's their fault.
Yeah.
If they haven't like come up to you, it's all.
And there are 12 students signed with you. Like Abby. Like I always just have to think for a second rather than just know. And I know I can get there, but you're on my medium list. Whereas like Alisar, ever since Dinosaur. Well, most of the students are like sweating up the night with it being so hot, and so it's at least nice to be cold sometimes.
I don't know about her.
I know, I know.
Or s-
Yeah. Is it very warm in here too, Rachel?
No.
No?
No, it's kind of neutral.
I know, until like after the
I heard like the science class was so warm in here.
Yeah, well, I mean, also you were just walking around with big coats and everything, like, it's just fun. And so then you're like hustling to get to class, and then you walk in and it's warm, and so, you know. So I'm going to give you about 30 more seconds and then we'll talk. I don't expect you to have gotten through all of them. Okay. Well, why don't we start with this middle one here? And I think for all of these, our strategy of retrosynthesis and kind of thinking backwards is going to be helpful. So we only know one reaction that makes an acetal, right? So why don't we do our synthetic disconnection and draw what the carbonyl form should be? So we're going to cut here, these two, and put hydrogens on, and then put a carbonyl where we cut. So it's going to look like this and this. Okay. Now this piece right here looks pretty close to this, right? So did we change oxidation levels?
Yeah.
Yeah, did we do an oxidation or reduction? Oxidation from level 1 to what level? 1 to 2. So oxidation, we use chromium, CrO3, and then going 1 to 2, we use pyridine. So that's 1. And then we need to do the acetal formation. So we know that we need to provide this specific alcohol because that was not there and it was in the product. So we have the diol, and then we need H+, and we don't need a step through. Cool. Okay. Enamine, did anyone try to do the kind of retrosynthesis breaking apart? So what we said our strategy was last time and I'll do it on the kind of general one, is we said we're going to cut here, put a hydrogen on to get our amine. We're going to pave over it, make it all single bonds on the other side, and a carbonyl. So let's try that in this actual molecule. So I'm going to cut here, CN bond, pave over this with a single bond, and then add a carbonyl. And then one thing back to my original one, I'll finish drawing this real quick. Here, there was a hydrogen that was there already, so I know that that's the other side of this carbonyl. It was an aldehyde. Okay. Well, getting from this to this, those seem like the same molecule, right? And we've just done some sort of reaction. What do we need to do to go from the alcohol to an aldehyde? Oxidation, chromium with pyridine, same as the one right before it. CrO3 pyridine, and that's going to get you here. And then, to form your enamine, all you would need to do is add your amine. And then, sometimes you might write pH around 5, like I think Serenia is partial of writing it that way, but like other professors and books don't do it that way. We're not going to grade whether or not you write pH 5, so you can if you want to, or don't if you don't. And then we don't need a third step. Okay, then let's talk about this last one. Yeah.
For that one, I was a reaction with
Yeah. Well, but the thing is, it has to be intermolecular to form a ring. Here we're breaking up a ring. And so it's not going to be as easy to think about it that way. No, we're going from this to this.
No, in the last question.
Oh.
Sorry. Like I was trying to figure out a way that we could have done because it's intermolecular. And it just
This is where knowing that enamine disconnection and being able to kind of think backwards here lets us know that that ring came from our amine. Because the only bond that was made from the nitrogen in the enamine formation is to the carbon that's next to the double bond. So the other bonds had to have already been there. So let's look at this one, and maybe let's try to think backwards from our product again. Because what's the oxidation level of the starting material? 3. What's the oxidation level of each of the carbons here? Also 3. And so it's kind of weird, like we've broken up the ring and we've stayed at the same oxidation level. But we know that we can make carboxylic acids from what other functional groups? So I'm just saying, how can we make a carboxylic acid using the reactions that we've learned today and like in lecture 5? Let's scroll back. So hypothetically, but that's kind of leading you down the wrong track, and I'm saying like using the redox reactions.
Okay.
Like this is the only way we know how to make an ester from something of a different functional group, like level. And so we can make it from alcohols or aldehydes typically. We're gonna, so in the wild, it would be like you might go down the wrong track and it takes a minute to figure it out and think about the possibilities, which is why you need to kind of brainstorm the different avenues. But for this one, I'm putting it in a specific section, and like this is why I kind of broke up the challenge problem box problems to kind of put them in ways to where it would be easier to see. So you're totally right that like you should think about the ester way of doing it, but I'm going to tell you that that way is going to require more than 3 steps.
So when we do a mountain, right, we will know at the end of this step or when we have a function breakdown, we know that.
Typically, or you'll have more steps than you have boxes. Yeah.
It is, it just theoretically is possible.
Yeah, it is possible. I don't think it's possible in 3 steps.
That's fine.
Yeah.
Honestly, because I would have done the ester and like
Totally.
stepping back and starting over. So.
Totally. And again, it's the thing of like an important part of doing box problems in synthesis is when you look at the functional group, being able to brainstorm all of the different types of reactions that you know that could make it. Just because it's so easy to get fixed on the first one that you think of that then this other route that's going to be probably a lot easier is just like lost. So what I'm going to do is I'm going to make them alcohols on both sides because I know I can turn alcohols into carboxylic acids. I could try aldehydes and doing a bunch of aldehyde chemistry as well. But I know I could like oxidize this and get all the way to the carboxylic acid. And so then we're thinking about getting from an ester to alcohol. What's the first thing you think of when you think about esters? Double addition to esters. We love Pavlovian conditioning.
Except on practice exam. That was so mean. Sorry.
I don't even remember it.
It was literally like an ester and like you were not supposed to double addition it.
How,
It was horrible.
how crazy. So we have an ester we're trying to get here. We have two oxygens in both of them, right? So maybe like one of these oxygens is going to be this one, and maybe one of them is going to be this one. It's kind of arbitrary because it's a symmetric molecule. It doesn't matter which one. But like, let's say we made the gray oxygen there. That would make this carbon, right? So what did we have to add to that carbon to take it from this ester form to this alcohol form? 2 hydrogens. That sounds like a double addition. And so what reagents should we use to double add hydrides?
So LiH.
Lithium aluminum hydride, exactly. So we use lithium aluminum hydride. What?
They make the alcohol.
Mm-hmm. So, and then 2, we have an H plus workup. And then once we make that, then step 3, we just need to oxidize. And to go all the way to 3, we use chromium with H2O. So it's kind of putting a lot of different pieces together. And I will say that like the box problems are only going to get more kind of interconnected of like the different lectures. And so each lecture that you're doing the homeworks for and kind of integrating, make sure you are not forgetting the tricks and tips that you were picking up along the way because they will come back. Yes, this is lecture 1 material.
Yeah.
This is the lecture 5 material. Or I said lecture 1, exam 1, I mean.
Yeah, but wait, but isn't just an X ester would be like more than 3 steps?
She was talking about like doing an ester to a carboxylic acid or vice versa
Oh.
in one step, which we are going to talk about next. So,
Oh, okay. We
Yeah.
can do that.
yeah.
And it's like there's only gonna get more reactions. Is there any way we can like group them together or like?
Yeah, and I'm going to talk a little bit about that. So, the next kind of topic today is going to be our big family, which are the CAD reactions. And so, what I've done here is I've kind of, at least on the left here, I just kind of like ossified, organized a page from the lecture notes to make it pretty to read. And I'm going to tell you the thing that is important for you to know from this page. The thing that is important is you need to know the relative levels of reactivities of these functional groups. Not this bottom one, this. The acid anhydride and the carboxylate are kind of just for fun, but these 1, 2, 3, 4, 5, you need to know what is more reactive than the other. So acid chloride is the absolute most reactive one that we can do. Then we have esters and carboxylic acids, which are about the same level of reactivity. Then less reactive than that is amides, less reactive than that is nitriles. The why of it is explained in terms of resonance and like the stability of the conjugate base, and we can go through all the reasons. I think that that's better studying and learning on your own because you've already seen this. And I'm going to kind of teach you how to be a practitioner with these reactions and kind of work with them. So the first big thing is knowing the order of reactivity of these functional groups. And then the main thing that we are going to be doing with these reactions is going to be using them for line reactions and synthesis. So like the mechanisms you were shown, they are in testable material, and you should not just like be like, okay, I'm not going to study any of those mechanisms. But these are going to show up much more often on box problems and synthesis than they are mechanisms. So with that, Serenia likes charts, I like webs. And I think presenting both of them to you, you can choose whatever visual medium is like better for you. But this is a way that I've kind of gone through and tried to organize the reactions from lecture in a kind of hopefully intuitive and somewhat clever way. So the big thing is, as we go from bottom to top, we have our reactivity trend for these functional groups baked in. So at the top, we have acid chloride, most reactive. These are about the same reactive. This one's less reactive, this one's the least reactive. So that's kind of baked in here. And then this, again, I don't expect any of you to have this down cold or memorized or even thought about since Tuesday's lecture, because y'all had something else to be working on. But at least for section today, what I want us to be comfortable with is learning to use this and see where we can get the information that we need to accomplish a chemical goal. So there are two kind of big principles that you need to understand to get these reactions together in terms of just the line reactions and how they're connected to each other. The first big idea is that you can always go from something more reactive to something less reactive. So like acid chloride, you can go to anything. You can always go from like ester down to amide, or carboxylic acid back down to amide. The one that's weird is nitrile, and it's because she's like the weird cousin of the CADs. Like, it technically is oxidation level of 3, but she doesn't have a carbonyl, and so she's invited to the reunion, but we don't like text her during the year. She's kind of just there. So these I tried to put in blue, the idea that we can always go down reactivity levels directly in one reaction. The other big thing is that everyone can interconvert with a carboxylic acid. So I put these all in red here. Like carboxylic acid, you can turn into any of these functional groups. You can turn any one of these functional groups into a carboxylic acid. So what that means is, let's say I was trying to go from an amide to an acid chloride. I would first ask myself, am I going up or down in reactivity? And which am I doing? Up. Well, I know I can't do that directly. So what I'm going to do is, my strategy is I'm going to go to a carboxylic acid and then go from carboxylic acid into acid chloride. And that's the process of doing all these questions. Like, I'll do one really quick of the box problems with you. So here, I'm going to do this one. What functional group is this? Amide, and then product, ester. Am I going up or down in reactivity? Up. Amides are less reactive than esters. So I know I need to go to a carboxylic acid. So what I would do is I would go, again, this is because I'm new to it, I'm still looking this. What's the reaction that takes me from amide to a carboxylic acid? I use H3O+. So I can go back and do that and put H3O+ here, and then write my little carboxylic acid that I get formed. And then I need to go from carboxylic acid to ester. So we would go to our little tree, and this is the Fischer esterification. So we would need an alcohol and acid, like H+. So the only question here is, what is our alcohol going to be? The way to find out is to cut the bond that goes to the carbonyl. So when you cut there, you will see that the alcohol that you needed to add was ethanol here. You cut and just add an H, and that's how you see the exact identity that you need to add. And then no step 3 needed. So that's the process of doing these types of questions. I'm going to give you a few minutes to work on some of these other ones here, and then we will go over them. But these are from challenge problems 3 and 4 in Skill Builders, page 6. So again, I'm hoping we can knock out some of the challenge problems and PSET stuff. And actually, I'm going to request that even if you use a paper problem set, you look at the section handout to see the questions, and I'm going to leave the web on the board so you don't have to keep scrolling, and you can just like look at the web on the board and then answer the questions on your section notes and such.
Is there a reason why acid chloride to carboxylic acid you didn't put that in blue?
I didn't put
Acid
what?
chloride to carboxylic acid, is there a reason that's not in the blue?
No, it's mostly just because like it is both blue and red. And I just kind of wanted to make it clear that this idea you can do anything with a carboxylic acid.
Okay.
It was just like a graphic design is my passion kind of thing. No one clocked the Comic Sans numbers for the exam group on the lecture hall. I was like, oh, I'm gonna be fun and print the pages in Comic Sans. It's dumb. It's dumb, but here we are.
Can you zoom in what's happening?
Like,
My vision is like,
I think that's all I can, or I can maybe do just a little bit. This is as big as I can get in and have everything. Or we can cut off the nitrile. We're gonna cut off the nitrile. Yeah. So we're gonna talk about her in a minute. She's a reagent that it's another one where we're just working at the line reaction level. And so she's a reagent that just couples together a carboxylic acid and an amine and pops out an amide. Yeah. And see, that is an example of like the lab TA who said like you don't need to memorize. They took a different version of this class. So when you do this version where you're doing synthesis, we're going to teach you reactions that you truly just have to memorize because it's a tool. Whereas when they do 17 during the fall, they're not doing synthesis. And so they are only learning reactions where they learn the mechanism. So
I think there should be two versions of this class.
there should be or
One
should.
with synthesis, one without
I mean, it might change.
this summer.
Are they gonna change it or?
Like now.
I think synthesis is the more useful one for if you're trying to be a doctor. In terms of like the skill set of like looking at tools that you have available, assessing an issue, trying to figure out a way to get there, and like to think through the consequences of each step, and also for practice dealing with a problem that's difficult to approach. I think that it is why, part of why OChem or Orgo is like a pre-med class, because that is a type of thinking that you will need to do as a doctor. The specifics of the reagents don't matter, but the skill, I think, is helpful.
Could do is do that. Synthesis is just like unnecessary.
Yeah. Whereas I think synthesis is the most fun, but
It's fun if you get it. If you don't get it, it's not fun.
oh, that's true.
It's like a math. Like I was like thinking about like what this is like, and it's like math and chemistry hybrid, like in the form of math proofs and like math.
It's like a really frustrating part of it.
Yeah, like it's like a math proof, but instead of having 4 operations, you have like 80 different mechanisms.
Huh. See, I don't think about that way out. I think Gen Chem is the math class. Like you're doing
No, but it's
calculation.
not the math of it; it's the proof of it. Like
Mhm.
trying to prove this
Logic.
equals this.
It's a geometry class. You're doing
Oh, that's
the
like
triangle
theorems.
congruences.
I haven't taken geometry in
Period. I'm gonna give like
What is the amount of reactions we're gonna have to learn after the reactions that we have?
you'll have between 80 and 90 for exam 2.
Good joke, Cole.
Like mechanisms or
Line reactions.
and mechanisms?
That means they're not.
I'm really not gonna touch the bees that are
Oh, strong
That's why I
choice.
force myself, or else I'll have to catch up with the day before the exam.
And that's much easier to do on a 15-page problem set than a 30-page problem set. Yeah.
Yeah, I'm gonna be cracked at it.
Go ahead.
I don't know whether to use
You can use either one. NaOH is going to give you a better yield. Like it's kind of like how we said hemiacetals form in base better, but they can also form an acid.
So I should just go with that.
I would go with NaOH, but both of them would get full points. Yep.
How long is scholarship for?
Back to the 30s. I don't remember. Mid-30s. I think 4 and 5 are mid-30s. 6 is 14 again.
Never 50 again.
Never 50 again. That's just one. Well, because we had to get you guys all on the same page, like from all the Gen Chem and stuff. But And again, just try to wrap up one more or one question at least in like the next 30 seconds, and then we're going to talk through a couple of them. Good. Let's look. So, which of these do you want to do together? We can either do the ones that you started working on, or we can do the ones at the bottom that you haven't seen yet that are on the problem set. What's your preference? Last one, what other one? I think I'm going to do the last two, just because I think that they're a little bit harder. And the second one we did, right? Oh, second to last. Okay. So, let's start off second to last. What functional group do we have? And the product, sorry. What functional group is in this molecule? An arine ring. What else? An amine. If only I knew reactions that made amines. If only I knew that there were only 2 reactions in this class that made amine. But I don't. So what to do? So what type of amine did we make? Primary, secondary, or tertiary? Tertiary. And if you go back to those 2 reactions that we talked about, the redox ones that make amines, the reduction of the nitrile will only make primary amines. So we know that we did not use this in that reaction, right? Because we formed a tertiary amine, and this thing only makes primary amines. So we have to have done this reaction. We have to have done the reduction of an amide here. So if we try to think backwards, what we're going to do is we're going to take this carbon by the nitrogen and plop a carbonyl on it. And that's how we're going to kind of think backwards and see what it was right before. So we know that this came from this amide. Just thinking backwards, we know it had to have been the amide reduction because we don't know anything else. And now we can think, how do we go from the acid chloride to an amide? Are we going up or down in reactivity? Down. And so does that mean that we can do it in one step, or do we have to go through a carboxylic acid? One step. So all we need to do is we need to add our amine, which we get by cutting right here and putting a little hydrogen on it. So we have this amine here, and then we use pyridine, and that's just from the reaction web. We use an amine and pyridine. Okay, that's going to get us there, and then to get from the amide down here to the amine, we use lithium hydride. Cool. Okay, and then for this bottom one, we start off using this thing called DCC. So let's just go and look on the web. Where do we see DCC? There's Waldo. So it takes a carboxylic acid to an amide. And all it does is it erases this and then puts on the amine to it, essentially. So let's do that and draw what we should get here if we do that step. So step 1 is going to produce. We are taking this amine NET2, so we need to have 2 ethyls on it. So in the mechanism, it is swallowed up, essentially. And it's because nitrogen is only neutral with 3 bonds, and it's easy to remove a hydrogen with an acid-base step.
So the DCC is responsible for
Yes, and that's one of the mechanisms that you're not responsible for.
I just had it in
Yeah. So we made this amide, and then we have lithium aluminum hydride. What does lithium aluminum hydride do to an amide? It gets rid of the carbonyl. It just erases it and makes our amine. So, if we just erase that carbonyl, what we are left with is this groovy little dude. So this is called triethylamine. It's also sometimes written as NET3. It's a common base. It's used a lot as a solvent. And it has a relative that's one of my favorite molecules, which is, what if you have 4 ethyls? Well, then you have a positive charge, and you're a little dancing dude. You see, he's just grooving. And so he's a tetraethylammonium man. Yeah. It's part of the lithium aluminum hydride with H plus workup. If we didn't do the H plus workup, then what we would be left with, again, you don't need to know the mechanism, but we would be left with, I believe, this nitrogen with a positive charge, and we need, no, that's wrong. We'd be left with like an enamine that then we would have to go and grab a hydrogen from and protonate it. But again, it's a mechanism thing. And this is just kind of a set. You always do H plus workup after lithium aluminum hydride. Okay. I'm at time, sadly, and I know that there's amino acids. If you want, I can do like a 5-minute rundown, or I can just leave you to do that on your own. Do you want me to do a 5-minute rundown of amino acid stuff?
You take all the time you need.
So truly, with the 10 a.m., I went through it and we did a challenge problem. I'm okay with doing that, but like I don't want to keep you here longer than like necessary. And so if you need to head out or if you want to head out, totally fine. But I just want to be like respectful of your time. But also, I feel like most of you would want to knock out a challenge problem. Is that okay? Okay. If anyone wants to walk out or stage a coup d'etat, overthrow me, please. So, amino acids, you've seen them in previous classes, probably a bio class, but now you have a little bit more context for what these functional groups mean and how they might react. So the amine group and the carboxylic acid group. pH of cells, they're in this Svita ion form where there's a positive and negative charge on the same molecule. But there are kind of a few big things that we need to do with it from our class perspective. One, you need to know how to make an amino acid from another functional group. And then 2, you need to know how to glue 2 amino acids together to make a dipeptide. That's what we care about for this class specifically. So let's first tackle that. How do we make an amino acid? There is this synthetic process called the Strecker amino acid synthesis that you are going to be responsible for that uses some of the reactions that you learned in lecture and combines it with like one weird step that makes it kind of all come together. But a Strecker amino acid synthesis starts with an aldehyde and turns an aldehyde into an amino acid. So here, whatever the R group is on the aldehyde becomes the R group of the amino acid. So in the first step of the Strecker, we have NaCN, NH4Cl. This NH4Cl is basically NH4+, and it is going to be doing an iminium formation here with the aldehyde. So this NH4 isn't a primary amine, but it has just as many hydrogens as a primary amine would. And so you're able to form an iminium intermediate in a solution. And then this is the weird part. This is the one thing that is not something that you've seen in a mechanism step before. We have NaCN, which is just like a CN minus in the solution. And the CN minus is going to go and attack the iminium. And that's going to get us to this intermediate here. So this reaction is forming the iminium, which we talked about at the very beginning, and then we add a cyanide. And what we're left with is we've kind of gotten halfway to our amino acid, right? We have our amino group, but instead of a carboxylic acid, we have a nitrile. Well, one of the carboxylic acid derivative reactions that you learned was going from a nitrile into a carboxylic acid. And so you do the nitrile hydrolysis mechanism with H3O+, and then you get your molecule. The last step here is neutralize, and that can be very broadly interpreted. So if I wanted to bring this at like biological pH, I would neutralize at pH 7, and I would get to that Svita ion form of the negative and positive. If I did in strong acid, then I would have just hydrogens on both sides. Or I could do it in more basic conditions and it have be like an NH2 neutral and an O minus. And so there are several different kind of stopping points that we can get to based on what the charge is. So no matter what, you should write neutralize, but then take it to whatever protonation state you need it to be at. Does that kind of make sense with the neutralize in terms of just the variation of the hydrogens on these two groups?
Can you repeat how we decide what the protonation station?
Typically, if you're trying to make a specific molecule. So if that molecule is charged, do it charged. If you need to use the nitrogen as like a nucleophile in the next step, make sure it's not positive. Yeah. So that's kind of goal 1, make an amino acid. Goal 2 is how do we make the dipeptide and make that kind of peptide bond, which is an amide bond. And we use this girl DCC. So her government name is dicyclohexylcarbodiimide. If you want to, just be like, don't ask, don't tell. You don't need to know this. You don't need to know the mechanism of this. You need to know that DCC is a matchmaker that will take a carboxylic acid, an amine, and go bloop, and make an amide. That's the extent that you need to know, because we're mostly, or almost exclusively, going to be using this for synthesis and then maybe some line reactions. So DCC will grab any amine it sees or any carboxylic acid and squeeze them together and make an amide. So the problem comes if we have options. So let's say I have peptide 1 and peptide 2, and they have different R groups here. And I shouldn't say peptide, amino acid 1 and amino acid 2. And I want to make the peptide that joins these two together like this, these two ends. And so I want to make this product. Well, if I just add DCC to this, it's going to make that product, certainly. But also, it's going to take the carboxylic acid of amino acid 2 and the amine of carboxylic acid. I'm saying wrong words. It's going to take the carboxylic acid of amino acid 2 and the amine of amino acid 1, and it's going to glue them together, and that's going to be this product. Or it's going to take 2 equivalents of this amino acid 2 and glue 2 of those together, or glue 2 of the amino acid 1s together. So we're going to get this mess. And so the solution is we need to protect whatever we don't want DCC to react with. So in exam 1, you learn how to protect really one thing. You learn to protect ketones and aldehydes as acetals. Here, you're going to learn 2 more things to protect. You're going to learn how to protect an amine and how to protect a carboxylic acid. So you protect an amine with this reagent called BOC2O. And the way that you write the protected version is you would write it as NH-BOC. You don't need to know the structure for this. If you want to see it, it's this big thing. And it basically like makes its own kind of amide bond in a very specific way. But again, this is just for synthesis, a strategy to protect our amine so that this won't do any other reactions that we don't want it to do. The way that we can deprotect it is using a reagent called TFA, trifluoroacetic acid, which again, you don't need to know this. This is just FYI in case you're interested. So BOC is how we protect the amine. Did you have a question?
Yeah, what do we protect all of them?
So you're only going to react with one of you're going to react with the molecules separately. So like let's say an amino acid 1 here, we didn't want to react with the amine, we would protect that one's amine. And then for this one, amino acid 2, we want to protect the carboxylic acid, we are going to react with that amino acid.
And that's before we like mix it together.
Exactly. So the way that we protect a carboxylic acid actually is one where you do know the mechanism. It's just forming an ester. So you do your little Fischer esterification here, turn it into an ester, and then we can remove it using the ester hydrolysis. And those are reactions just from like the previous page. So we have protected the things that we do not want to react, and now DCC has no option but to do the one that we want it to do. And so we make the bond that we desired. We've gotten the kind of peptide backbone all set, but we still have our protecting groups on. So we just need to deprotect them. So we remove BOC with the TFA, and then we do the ester hydrolysis, and then we get to the product. So this is kind of a lot of steps here, but it's really a structure for a synthesis that is kind of nice, because there are like 2 steps to protect, 1 step DCC, 3 steps deprotect. That's 6 steps on a synthesis, and your synthesis questions are typically never more than like 10 or 12 like steps. And so that's like half of the synthesis that you know the general structure for, which is really nice compared to one where it's like, oh, you're taking us on a journey. Okay. So there will be a synthesis question that's a DCC synthesis on either exam 2 or the final exam. So if you don't see it in exam 2, it will show up on the final. Therapist, bok chicken isn't real. Bok chicken can't hurt you. There she is.
Did you make that meal?
I didn't make it, I found it. I have made some.
That one.
This is also bok, free amine, unwanted side reactions. Which, like, that's the vibe. That's the vibe. So, correct. And I typically pitch for the DCC to be on the final, just because it's a little easier and giving you more points at the end, you know? But we'll see. So let's look at challenge problem 4, or challenge problem 5, sorry. And let's try to break this down and kind of see how these come together. I think I can do it in like 7 minutes, and then we can get through it. So the first thing, how do we recognize something as a DCC problem? We see an amino acid, or we see like this peptide bond kind of structure at the end. So we know that we've kind of glued these together, and what we're going to try to do is see how these story materials kind of map onto the product. So what is something in the story materials that you feel confident you know where it is in the product? Yeah, the phenyl group. This is pretty much definitely here, right? Okay. And then where do you think this glycine is? Like if I just do kind of that structure. Yeah, like at the bottom, the thing that just like doesn't have anything there. Okay. Well, and then that means these could be kind of a potential, like, our 2 amino acids that join together. So our like special amide bond that DCC made is going to be here. And specifically, this is the amide bond. But why don't we use our kind of retrosynthesis to think back, what are our 2 pieces that we're gluing together going to look like? So if we kind of split this up, and this is just before DCC, on the left, this side, when we split it, is going to become our carboxylic acid side. And our right side was the amine side. I'm just going to abbreviate the phenyl ring with a PH. So we know that we want this and this to be our reactive sides that come together. Well, that means that we need to protect the other things. So we need to lock down the other side. And what is weird about this amino acid here? There's no carboxylic acid. There's an amide there. And so this is something that we would know of, like amide. Do we know how to make an amide from a carboxylic acid? Yeah. This is one of our, like, just CAD inner conversions. We can make an amide from a carboxylic acid? Sure, no problem. So, just something to think about, that at some point we'll need to make an amide, but that's not going to be our kind of core structure of the synthesis problem, right? So let's see. This molecule here is straight up glycine. We don't need to change anything about it, but we need to turn this thing, which is what functional group? An alcohol, into a whole amino acid, basically. So what's our synthesis pathway that we know that makes an amino acid? DCC joins together amino acids, and the one we talked about right before that was how to make an amino acid.
Oh, the structure thing.
Yes, the one on the board.
Oh, shoot, sorry.
No, it's all good. I think y'all were like so in the sauce that you didn't see me like. So we need to do this, and what functional group do we need to start with for a Strecker? Aldehyde. And we have an alcohol. Can we make an alcohol into an aldehyde? How do we do it? You need to do an oxidation. So an aldehyde is oxidation level 2, and an alcohol is oxidation level 1. And that's how we flag that we need to go between them. And so using those redox line reactions from earlier. Okay, and now we can start to do the Strecker. So y'all looking at your notes, what is the first step of the Strecker? And the reagent, sorry, to make the aldehyde, I forgot to write, 0,3 pyridine. Yeah, so what's the first step of the Strecker? Like what reagents do we need to add? What are the reagents that we need to put on the arrow? Yes. Mm-hmm. If you were doing a mechanism of it, you're totally right. You're thinking through the full mechanism of it. But here, for a synthesis, we only care about the line reaction level. So how do I draw what the next product should be? Like, what does the first step replace the carbonyl with? CN, and what's the other one instead?
I'm thinking about cyano, whatever.
Yeah, we're going to install the amine group there, so we still have the hydrogen down here. We install the NH2, and we install a CN. Okay. And then the next steps are what? Mm-hmm. And again, y'all should not be at the phase, and you're studying with this yet, where you should just know that off the top of your head, but you should know where to look in your notes to get it. And you should know that that is a thing that you will be studying and kind of internalizing. Okay, so that is going to hydrolyze that cyanide, CN, and make it into a carboxylic acid. So we have the NH2 stay over here, and then the carbon that was in the CN is going to be the carbon here, and that's going to become the base of a carboxylic acid. Am I going too fast? Have I lost people?
No, somebody.
Mm.
I didn't do these two separate things. The two studying. I protected it and then I did it. It's not
Okay.
fun.
I'll have to see.
Well, so I didn't know you could do it in two separate.
One and two.
So I'm doing this to make it clear that it's the Strecker synthesis, which is this
Okay.
3-step process.
Yeah.
Here, you didn't need to put numbers there, but this, if you do 2 of them, you would need to do 1, 2. Yeah. Okay, so now we have this bad boy. Well, we need to do our protecting then. Like, we're ready, we have 2 amino acids, so we need to shut down the things that we don't want to react, and then let the 2 things that we do want to react with GCC. So in this molecule, we said that we wanted to shut down the carboxylic acid, right? So how do we protect a carboxylic acid?
Acetone?
That's for ketones aldehydes. Yeah, we turn it into an ester. So what's everyone's favorite alcohol? Sure, methanol. So MEOH H plus. And then I'm going to write this in a way that kind of looks closer to what we had drawn down there. So NH2, O, and we would have OMe, and then our phenyl. Okay, so we have locked down this, so only this is going to react. And then on our glycine, we want this to react, but we need to lock down that amine. And how do we protect an amine? BOC2O, yes. So we keep the carboxylic acid side totally the same, and our amine becomes NH-BOC. So we have this reactive side, and we've shut this down. So are we ready to combine with GCC? Does DCC have any other options to choose and do things that we don't want it to do? No. So we would draw something to connect both of them. I might write combine just to make it explicit. If you didn't write it, but you did have this kind of arrow or line kind of connecting them, that's fine. Combine and use DCC. And then we're going to have most of our peptide. We're in the home stretch here. So we've made that peptide bond that we were after, but we still have protecting groups. So this is the structure of our DCC census where we need to deprotect. Okay. So we need to deprotect, and then also we still have this amide thing to deal with, right? Like somehow this needs to be NH2 on the end. So which do you think that we should do first? Should we deprotect everything, or should we do the amide first, or should we deprotect one thing? Oh my gosh. Yes. So let's try it. Ester to amide, are we going up or down in reactivity? We're going down, right? And so if we're going down in reactivity, can we do that in one step, or do we have to go to a carboxylic acid? One step. So let's do it. So ester to amide, what we use, and this is just from the web, is we use an amine and pyridine, or you can just use excess amine. That's a different way to write it. So what amine do we need to use here to just get NH2 on the end? NH3. Because if it had another carbon chain on it, that carbon would still be there in the product, right? So we want NH3 and pyridine, and that is going to make our next to last structure. And then finally, we have to deprotect Bach. And so what do we use for that? TFA, oh my gosh, thank you. Oh, I just thought of a really stupid mnemonic that a friend uses to remember it. TFA kind of sounds like Tina Fey. And she just said, well, Tina Fey hates chickens. And Bach 2.0 has like a chicken feed. And it's just so absurd that it really does stick. Tina Fey hates chickens. So how do you remove Bach? Tina Fey drives away the Bach chicken. But with that, we've done the synthesis. So I went over time a good deal, more than I wanted to. I thought I could do the synthesis in like 7 minutes, but here we are. I hope you have a good weekend. Please rest. Please take some time to like not do organic chemistry. You have a whole piece set, but it's a half piece set. And we have Normal Helper Monday, the quiz due tonight. I'll stick around for any questions that you have, but thank you for coming to section, and I also hope that I didn't waste your time by going over. Yeah.